So in this video, we're going to be looking at transfer functions. And a transfer function is a mathematical function that describes the output response of a system based on the input. And what we want to focus on in this video is we wanted to look at the key points that we can tell about the system. And so one of those is the steady state. The steady state basically describes that after the transient response, after all the dynamic changes have settled. So what we're going to be doing is we're going to be looking at a step response, and then we want to see how the system behaves as you apply a step change to it. We want to see how that's going to apply and affect the system. And so the first thing we typically look at is the final value of that and see whether the system has settled down at a steady state or if it's actually still increasing or something along those lines. So we want to look at the steady state. And then we also then we're going to concentrate more on how did the system actually respond to that. So we're going to look at the transient responses. And so the transient responses, the biggest things we want to look at are the rise time. How fast did the system actually start moving to that change? And then we want to also look at the settling time. So after the system started moving, okay, how long did it take to actually get it to settle down? And then did it overshoot that final steady state value? Okay, so FV here is the final value. So we want to look at what was the maximum value minus the final value, and if that is a positive number, then that's what we call overshoot, and we want to see how much overshoot we have. So these are certain parts that we pick out of the transient response to see how the system is responding to that step change. Now the rise time, as you can see here, the rise time is defined as going between 10% and 90% of the final value. I'm sorry, it's a typo there. It should say final value, not first time. So the rise time is the time between 10% and 90% of the final value. And the settling time is the time that it gets within 90% of the final value and stays there. So what this means, the reason I say within, it's really should be within plus or minus 10% of the final value. So it gets above 90% or below 110%. So if there's overshoot, it may actually be over the final value and coming back down. So with settling time, we need to look at when it gets within 10% of that final value. So plus or minus 10% of that is the settling time. All right, so we use this like what we're going to be looking at, a couple of things we'll be looking at there for this rise time is that 10%, we want to see at what time, right? We need to be looking at what time it passes 10%. So that's a threshold. That's a 10% threshold. And then also the 90% threshold. What time does it pass through that? Okay, so here is a underdamped second order response to a transfer function. We'll look at the actual code of the transfer function here in a little bit, but this is a response. So you can see here what we did was we applied a step response. So that was a unit step. So notice this value is at 0.7. All right, so the unit step we actually gave it to, it was way above here off the graph at 1. It was a unit step, a step of 1, but it only went to 1/2. So the final value actually is coming in here at 0.5 or 1/2 of the unit step. And this is seconds down here. I haven't actually added my label to the graph yet for the horizontal axis or the independent axis, but it's in seconds. And so when we look at this, we see that, okay, well, here's my final value. And so the final value is 1/2. And so you can clearly see then that we've overshot. Okay, so this point here is what we call overshoot. Okay, so we've overshot this. And so the overshoot, again, as we said before, the overshoot is given in a percentage. So it's 100 times the maximum value here. Okay, I'll just abbreviate the max value minus the final value divided by the final value. And then again, we multiply that times 100% to make it a percentage. Okay. And so in this case here, you can see I'm getting up here at about 67. Okay, but I'm not quite sure exactly what that value is. So what we're going to do is we're going to use MATLAB here, or Octave. Actually, I'm going to use Octave in this video to find out exactly what this maximum value here is. We also want to see the rise time. The rise time, if this is about 90% right here, okay, so this is 90% of the final value, and say this is about 10% of the final value. So the rise time is going to be looking at the time. How long did it take? How long did it take to reach, to move between this 10% threshold and this 90% threshold? How long did it take to do that? And so that is what we call the rise time. This is supposed to be an R here. Okay, the rise time. And then we have the settling time. The settling time is how long it takes for it to get within that 90% or plus or minus 10% of the value. So it may actually be up here at 110% or 90%. So when we're in between here, and we stay in between. So you see at this point here, it looks, of course, depending on how I drew my line, but it looks like maybe it actually dropped below. All right, so right here it looks like it was dropping below, so that would not count. So we look at the time for the settling time. We're going to look at the time that it started at time t equals 0 to this point here where it actually gets within this plus or minus 10% of the final value and stays there. Okay, so that's what we're looking at. All right, so if we look at our code here, again, I'm actually going to be using Octave here, but so I'm just starting out like normal. I'm going to clear all my variables out, and I'm also going to clear the command window. CLC's clear the command window, and I'm going to use a figure to do the plot. So I'm going to call that figure and make sure it's cleared out, and then I'm setting my denominator here. So in this case, my function, or my transfer function, is actually is 4 divided by s squared plus 2s plus 8. Okay, so the coefficients for the denominator are 1, 2, and 8. And actually, I kind of didn't want it to go to 1 for this video, so I just made it 1/2 of that. So that's why my num here, num is actually being defined as the 8 divided by 2, just so I'd have a nice round final value of 1/2, if you call that a round value. All right, so, but I'm building up using my numerator and my denominator. I am building up the transfer function using the control toolbox. I'm building up the transfer function using a numerator and denominator polynomial coefficient vectors. And then I'm setting my time step and building my time vector to plot. And then I'm going to use the built-in step function. Again, that's part of the control toolbox. And it's going to do the step response. And this is my step response. So that step function is applying a unit step. So it's going up to 1, which is technically up here off the screen, right? That's the driving value is going to 1, but my final value is actually only going to 1/2. All right, and then I'm going to plot that. So I'm just going to plot that. Now I'm plotting it as a subplot here at the moment, so it's just at the top of the figure, so I got room for the bottom of the figure. So at the bottom of the figure, what I want to actually plot is the velocity term. All right, and so the way we do that, okay, so right here I'm going to plot the velocity now, or the first derivative, also known as x dot, okay? And so I'm going to say the x dot, okay, is equal to, and we've done this before, this is equal to x of 2 to the n. So remember, x is my output vector. X is my output vector of my step response. And so what I need to do is I need to just find out how fast that is changing. So I just do 1 comma end minus 1. So this is a vector. This vector is going to be 1 unit less. All right. So now remember, you can always just take these commands and put them over to your command window and execute them and see what they do. All right, so there I executed that. Now I'm going to run the whos command, and I'm going to look at my time vector, my x vector, and my x dot vector. Okay, so you got to make use of this whos command and look at your variables and see what's going on. So you see here's my time vector, and then you see the x. Now notice they're both vectors, but the t is actually a row vector, but the step response returns the x as a column vector, but that doesn't really matter. What's important is that they're both 601 elements. But x dot is only 600 elements, so it's 1 shy. So if I want to plot x dot, I'm going to have to shorten my t vector. Okay, I'm going to have to drop off either one at the beginning or one at the end. And so usually I drop off the t equals 0 piece. And so now I'm going to do a subplot, and I'm going to plot, the bottom plot now is going to be my x dot term. And so I'm going to plot t, but I'm just going to go from 2 to the end and then plot my x dot. Okay, and so I'm going to just plot this as a second plot. And this is enough. Before, you don't want to try to do too much. Just do a little bit and then run it and see how it runs here. All right, and so I ran it, and we flip over to our figure, and I don't see my plot. Okay, so did I have an error message there? No. All right, so let me look at this. Maybe I have another figure window open. All right, so here is my plot, and so we have x dot then is drawn down here at the bottom. Okay, so we have just our x and our x dot, and so that's how we can get the derivative, and we can see how fast the system is changing. Okay, from the step response, right? So anytime that you have a vector, you can always get the derivative of the vector by just seeing how fast it changes. And I can divide by the time step because I know that my my time vector has a constant time step, so I can do that. All right, so now let's find out number one, what is the final value? So I'm gonna look for the final value. So my final value is equal to the max, or if we look at our response, let's look at our response here. You see, right, we're looking for the final value, and sometimes it may be bouncing around a little bit right here. And so just to be safe, I'm going to average the last 10 values. So I'm going to use the mean or the average command of x, the last value minus 10, okay, to the last value. So I'm just going to average that to get the final value. And then I'm also going to get the max value. So I'm going to get the max value of x using the max function, and that I just pass it the entire x function. So now we can get the percent overshoot. We can get the overshoot, which is equal to the max minus the final value, okay, divided by the final value times 100. So I'll multiply times 100 first, and then divide by my final value. So that is my percent overshoot. So now we have these values. So I'm going to go ahead and I'm going to plot a line for my axis. Now I want to go actually back up to my first subplot. Okay, so I'm going to recall and say I want to go back to my first plot. Okay, and I'm going to get the axis of that. So remember, your axis values are actually xmin, comma xmax, comma ymin, comma ymax. Okay, and so I'm going to call the axis so I get my min and max values. So I have those stored, and then I can use them to plot. So so now I want to plot a line. So I'm going to plot a final value line. Okay. So I'm going to turn hold on. Let's make sure I don't lose my plot, and then I'm going to plot my xmin, comma xmax, because this is going to be a vertical line. And then I'm going to plot that is going to be my final value, and I need 2 points, so I'll just make a vector of 1, 1. Okay, or if you wanted to, you could just type in your final value variable. Okay, so this is going to be a horizontal line, and I'm going to make that blue, but I'm going to make it a dotted line. Okay, so that's just going to be my final value here. So again, I created a little bit of little code. I'm going to run it, and we see I'm getting an error message. So you don't want to like try to write hundreds of lines of code and find out you got hundreds of typos. Write a couple of lines of code and check for typos and fix them. Okay, so look at your command window and look at your error message. It was the mean command. All right, I was missing a parenthesis on it. Okay. All right, so I'll fix that, run it again, make sure I don't have any other typos. Oh, so got another one. On line 33, second undefined return list. What's that? Line 33. Okay, I don't know, it seems like some versions of the axis command, some versions of Octave doesn't like you to break it up into the 4 elements. Okay, so if that's the case, then I can just plot. It's actually, a lot of times I like to do this anyhow because it makes my X plot a little bit easier. I'm just going to take the first 2 elements out of my axis and plot those. All right, so let's see if I got any others. Oop. Boy, I made a lot of mistakes on this. All right, so now I don't have any error messages here. And now you see, here's my dotted line showing that final value at 0.5 that on there. So let's go ahead and label that. Okay, so using the text function, we can just go ahead and plot that. And so we can just plot this using the text function. Okay, where are we at here? So I'm going to use the text function here, and I'm just going to start it at the far left. So, but I don't want to start it right at 0 because it'll be right at the axis. So I'm going to just start it at like 0.1 seconds in the horizontal, and I want it to be above my final value dotted line. So I'm going, a 1 times final value would be right on the line. So I want it to be above the line. So I'm just going to make it about 5%. So 1.05, that's 5% above the final value. And then we're going to use the sprintf function to take the final value, whatever it is, right? We think it's 0.5 from the graph, but this will be more accurate. I'm going to use 2 decimal points, and I'm going to print that in the color blue. And so now when we look at our plot here, you can see that we've actually labeled the final value there on the graph. Okay, so it just kind of annotates the graph, showing us in a very professional manner what that value is. We could also do a line for the max value. And so I've already calculated the max value. But here, what I'm going to do is, a lot of times I like to draw a tangent line to the top of that. So I'm actually going to plot a line for the max value here. I'm going to plot the line from the t, where the time, so I haven't found out when the time occurs, so I'm going to have to find that out. So when does it hit this maximum value? At what time? Okay, and so I'm not quite sure what time it is, but I know what the max value is because that is the value, right, from in this variable that I created in my code here. So I said, give me the max value. So there's my max value. So now I'm going to use the index function. So I'm going to use the index. I'm going to create a variable. I just call it idx for index. And I'm going to use the find command to find out where x is exactly equal to that maximum value. Okay, and so that occurs at index 120. So if we look at our time vector at that index, that occurs at 1.19 seconds. All right, so we can just take this code now and just program this code right into our M file to find out and then plot that line. So let me just paste this in here, clean it up a little bit. Okay, so that's Okay, so t index, so that'll be t at max x. Okay, so I'm going to store that into this variable. Got an extra x in there. Put my semicolons on there so they don't display. But now I'm going to plot a line. Okay, so I'm going to plot a line from the t-min. Okay, so from the beginning t, I'm going to go ahead and plot a line to that maximum point there. Okay, and again, that's going to just be a horizontal line. And I want that to be a dotted line also. So I'm going to plot this line at max. And then I'm going to put the text in there. Okay, and the text, I guess I'll put the text pretty much just the way it was before there too. Okay, but I'm going to put in my percent overshoot here. So I'm going to put my overshoot value to tell me what the percentage is. So I need a percent sign in here. So I'm just going to put in like percent because notice 1% is to tell it to use a floating point. So if you actually want a percent sign, what you do is you double them up. Okay. And so again, I got a couple lines of code here. So let's just go ahead and run this thing. And again, I got a typo. Okay. So look at your command window. T-min is undefined. Yeah, that's right. I forgot it didn't take the t-min. So that's just my first axis value. That's my t-min, okay, and so that's coming from my axis value, and I just want the first one there. All right, so we'll run that one. And so now you can see that we've labeled that, and we got 30.16% overshoot. Okay, and so we can label those. All right, so similarly, we want to find like the rise time. So the first thing we got to do is find x 10%. Okay, so x 10% is equal to 0.1 times x of the final value. Okay, and then we want to look at the 90%. So 0.9 times the final value. And then we want to, well, again, let's look at this in the command window. Okay, so if we run these two lines of code here in our command window, all right, we get x10 and x90. All right, so the question now becomes, when is x greater than x10? So I'm going to say, again, I'm going to use my index. I'm going to reuse the same variable, and I'm going to say find x greater than or equal to x 10%. Now, when I do this, I get a lot of hits, but I want to know when it first occurs. So we just want to look at the first index. So this index has, several hundred at least of a match, but I only want to look at the first one. So we'll do the find. Okay, so we'll look at the index here. So we'll do this index equals find x greater than or equal to x10. And then we're going to get that value of x10, okay, is going to be, or not the value, we know the value already. I calculated that value right here. All right, but we want to know at what time does that occur? Okay, so, well, what time does that occur? That occurs at t of the very first index. Okay, so t at the first index, 1 there. And then we want to do the exact same for the 90. Okay, so I'm just going to copy these couple of lines. And just change the 10 to a 90. Okay, and I don't need that line, that's redundant. So now I want to go ahead and just plot those. Okay, so I'm just going to kind of plot those as vertical lines because I'm really concerned about the time for those lines. Okay, so I'm concerned about the time, and so I'm going to plot a couple of vertical lines. So I'm going to plot a vertical line. So my tx10, tx10, so the time doesn't change. And the height is going to go from 0 to x10. Okay. And just to make it show up, I'm going to change the color of it here. All right. And then I'm going to do the same thing for my 90 line. So I'm just going to copy this and put the 90 lines in there. Okay. And then we can print out that value using, so so I'm going to plot here at time tx10. I'm going to plot this now, and I want to plot it. I want to see. I'm not sure if I can do this. I want to plot it just below the line. So I'm going to do a minus x. Okay, because my time, my y value is actually starting at 0. It doesn't go below 0, but I want to put this right below there. Or actually, I guess I can put it right above it. Let's just put it right above, because my lines aren't going below. And so we're going to plot, this is the rise time. T, lowercase t, underscore r for rise. Okay, and that's going to be my rise time. Now the rise time is time x90 minus time x10. That's my rise time. All right, and so I'm just going to run that. Come back over to my code, run my code. Remember, if you type in a key or two, then you can recall your command and run that. And now you can see there are my red lines, and there's my rise time. And actually that rise time, I just plot it right at 0, I guess. And I'm going to change the color of it to red. Get it on the screen here. Change the color to red. Save it. Rerun this. Right? And so then now you can see there's my rise time. And I had a percentage on there because I just copied it from the previous, so it should be in seconds. Okay, so let me put an S there for seconds. Okay, so the T rise is 0.5 seconds. So it takes half a second to go from 10% to 90% of the final value. All right, now if you notice there though, if I don't know if I zoom in on here, well, it doesn't really show up too well when I try to zoom in on that, but the T is right on that dotted line. So an easy way to fix that using your sprintf is throw in a space. So you, instead of just starting your text, throw in a space to just give you a little bit of room before that dotted line so you don't kind of smush them together there. So just lead off with a space. All right, so but there is how we can find the rise time, the percent overshoot, the final value, find all these things from the actual response. So we're pulling these out from the actual response. And we could do the same thing for the settling time.